Recording in progress.
Okay, you can see the screen and hear me, right? Okay, so yeah, this recitation is on RNNs. The previous week, I think Prof has been covering sequence networks or sequence models in the class. I think he's covered RNNs, the problems of RNNs, the stability, LSTMs, etc. Today, we are going to go over that once again on it in a different way. And we are also going to go through a code walkthrough to understand how these networks can be implemented using PyTorch, which will be useful for your further homeworks. So let's start off. Uh, so first of all, like what is the need for RNNs, right? So you've dealt with images so far, right? Where there is no sense of sequentiality. Like if an apple is on one corner of the image or the other corner of the image, there's no saying this apple came after this apple, right? It's all in the same time dimension. It's just a different spatial dimension. But on the other hand, you also dealt with 1D CNNs, which actually dealt with time data. They were called time delay neural networks, right? So they can deal with sequential data like text, music, speech, etc. But 1D CNNs have certain limitations because they act on specific localizations. So they can only capture short range relationships or dependencies depending on the kernel size. And there is that limitation of not being able to capture relationships that happen or occur much earlier in the time dimension or much further away in the time dimension. So this is where RNNs come in place. So just like CNNs, there was one small block going over different parts of the image. RNNs are also one single network that go over the input at each time step, but with the addition that they also take in as input the computations that have been done over the previous time steps. So at any time step, the state of an RNN has information for all the time steps that occurred before that. So that is how RNNs are able to capture relationships throughout the sequence instead of a small localized place in the sequence. Now, 1D CNNs, so this is like these are some examples of sequential data. As I said, there can be audio, speech, there can be video, which is like multimodal in terms of visuals as well as audio, but it's still temporal in nature. And there is text, of course. Um, can we go to the next slide, ma'am? Yeah. Uh, So just before we go to the different kinds of RNN, I just want to bring out a few distinctions that you can keep in mind while dealing with 1D CNN versus, say, RNN. So as I said, 1D CNNs plays the same filter in different parts of the sequence. And that means that a lot of the computations can happen parallelly. So 1D CNNs are very computationally efficient. However, they have that limitation of not being able to capture extremely long-range dependencies. RNNs, on the other hand, are sequential in nature. So you cannot compute the output or the state of an RNN at t equals 10 till you've computed the states till t equals 0 to 9. So they are computationally inefficient, but they have the advantage of being able to capture long-range dependencies. So these are some trade-offs that you can keep in mind. And just because of the intrinsic nature of text, speech, these things, the long range of dependencies that these modalities exhibit, RNNs or sequence models are a more common choice than 1D CNNs for modeling this kind of data. So this kind of data or these problems can be of different kinds. So like the one-to-one case is like very simple. So in the image world, you have one image which goes to one of several classes. So that's a one-to-one kind of problem. There is one input and one output. One to many is different. So you may start with like one word. It's like you give Chat GPT one word, say king, and then it generates 10 words after that. So language modeling is a common one to many kind of scenario, or a many to many even, where you give one input and it gives outputs at different time steps. It can also be many to one, which is classification of a sequence. So in classification of an image or classification of a single word, it was one to one, but you can have a full sentence, a full sequence of different words, and it can have one label. So sentiment classification is a different thing, where I can give an input like I like this movie. This is a 4 time step input, and there's one output which is positive, right? So that's many to one. Then there's many to many. So this is the classic language modeling example, or even translation example, where the input is, say, a sequence in English, and the output is a sequence in a totally different language. So that's many to many. This is probably the most common use case of sequence models that you've come across recently. And then there's many to many, which is a little more complex. That is when there is videos and you have to give say image like video captioning or something. So you have temporal data and you have to give outputs at each time step synchronously and not wait for the entire video to get over, because captioning has to be done in real time. So that's many to many, or even object tracking or things like that. So there are all these different kinds of things which can be dealt with in the same way using RNNs, a bit different with changes in how you train them. So this was a general introduction to RNNs. And now going deeper into what RNNs, how they actually act. So as I said in the beginning, there's one single unit that acts on each time step. So this unit not only takes the input at that time step, which is xt that you see down below, but it also takes the inputs or the computation or the state. It's called different things like hidden state, someone calls it RNN state or things like that, which essentially the state that has information of all the time steps before that. So when you go to the next time step, you feed in the input at that time step and also the state that you've computed so far. So that is the that going back into A, which means that HT would be fed back to A on the next time step, in addition to XT plus 1 of the next time step. So that is why it's called recurrent neural networks, because the output of at one time step keeps getting fed into the same network at the next time step. That's why it's called recurrent. And the way you back propagate through this is more different. It's different from other networks because there is this temporal nature, where there is self-dependency because of this loop. So that's called back propagation through time, which Mia will be covering in the next slides. Mia, you can go ahead with this. No?
Okay. Okay. I'll just skip this one because I didn't know that. Okay. So as a slight detour, and before getting to any examples, I just want to make sure there's some background in case there's questions on, but this will be covered in lecture after spring break. So how do you represent text to a neural network? There's many ways to handle this and encode it to the neural network. You don't pass literal strings, but you pass it as a float or an integer number values because it has to be able to do the math with it. So one of the ways they do it is to create something like a dictionary, which is all the words that are possible that you could have. And you could say, let's give an index to every word in it. So say it's in order here, the song lyrics, never gonna give you up. Seeing never is the first word. And we see the one here saying that it is the first word. So you can represent that as one hot encoding, which is what this is called. One of the issues with this, you can imagine in the space that it occupies, if this is a vector in some space, it should be a 5-dimensional space for 5 words, but the space will increase linearly with the number of unique words you encounter, and this can get really inefficient. Another way of doing this is you can encode it as an integer or a word embedding. The word embedding is a matrix that operates on something like the one-hot embedding and transform it into a denser vector of some reduced dimensionality. This is interesting because it's efficient for space representation, and second, because of the locations in that space, you can have things that have relationships with each other. So what you see here on the right, they're from GLOVE, from Stanford, and GLOVE is an embedding system that takes these words and creates vectors out of them in some space. And what you'll notice at the top is that the relationship between man and woman in English is similar to the relationship between uncle and aunt relative to each other. Where in this space, just keep in mind it's a many-dimensional space and not just 2 dimensions. It's just projected onto 2 dimensions here. So you'll notice that man and woman, sir and madam, have similar relationships to each other, as they should. And the bottom also shows here like slower, slower, slowest, short, shorter, shortest. So this is a way to represent a relative meaning with words and have so they can carry more information into the network to be used. When you output this, you're going to output a word, but it's not quite a word that it produces. What it produces is some numbers representing the probability of the next word. So with the song lyrics, never gonna give you up, we're trying to guess the up word underlined here. N equals 5, so there should be a probability distribution with a vector where each index is the value probability of that word showing up. So that at the end of the sentence, you would want the probabilities to be weighted heavily on the last word. The other words might exist after this word you, but we want the highest probabilities. we want up to be the highest probability because it's the word that's supposed to be predicted there, like in this example. Another example would be trying to create that sequence. In this case, you'll notice that when it's trying to predict the word down, there are two possible words it could be predicting based on this data that we have so far. Sometimes you can have an equal probability between options like here, but memory does play a role in how the predictions come about. Okay, so back to unrolling. I want to give a couple examples for prediction and generation, but to preface the next images, I have a different representation of how the unrolled RNNs look. Here I've put the X0 input with H0 output, but to me this is more like transcription, where you maybe hear some sound and then that first sound in the time step should correspond to the first word or first phoneme in that speech data. Whereas here for text generation, I'm taking the first word X0 as input, and you wouldn't be producing the same word in the next step, but instead you'll predict or generate something. So I'm showing it as H1 here. Okay, so let's go through a prediction example. Let's say you know the phrase on the bottom and you're going to pass the network this phrase. We're going to predict up. We give it an initialized hidden state, which can be zeros, and we'll give it an encoding of the word never, like an embedding. Never is going to produce some hidden state, which is equal to the probability of the first output, because this is the 0th input, and giving this an initialized hidden state with the word never. Because we already have going here, or gonna, we're gonna pass this hidden state, and we can also give it gonna. And here we give it the ground truth of the next word, and it will also output the second hidden state. That's the probability of word 2, given that first hidden state, and gonna. And what you'll notice is that these hidden states are some combination or calculation that aggregates the information from previous time steps. However, the full information is starting to be combined, and the percentage of the first 0th output and the hidden state as it goes through might start to diminish as you try to remember more and more things. And this is the nature of what happens when you pack information into a finite vector. You don't have infinite space to hold that information, and there are certain things that will happen because of that. The much earlier time steps will begin to diminish, and it actually may not know what to put in the final step. So moving forward, we get through, so it has the full hidden state and will produce the probability of word 4, which is hopefully up with the highest probability. H4 is not the word up or an integer value, but a vector where each index is the probability of the word at that particular index. And after training, it would ideally be a high probability. But if never is the 0th item in the index, never should be a low probability here at the end. Okay, let's talk about a generation example where we're not going to stop after the first prediction. So here we have something, and it produces its probability given the first word in the initialized hidden state. It's going to take in the next word, have this, and it's going to pass H2. So how would it continue? You can take the max of H2, and hopefully the max probability item in H2, the hidden state, is the word 2, and you would hope that there is then enough information to give out the next word. And you can continue to generate this way more and more. Here's a quick image of what backprop in RNNs may look like. As you go through, obviously you know that for a single cell, it will backprop through its own self, linear layers and activations. But the information has to go back from the next output's loss, and that also has to go through the previous, and it's chaining all the way through. Although this cell is an RNN that is only 1 layer deep here, you can see that by the time you get back to the beginning, it kind of acts like it was 4 layers deep for certain parts of the gradients, at least for the sequential dependence portion. And it acts like a much deeper network for the sequential, for this part of the gradient, and it creates certain problems for learning. And this can actually happen in both directions because it also simulates a deep network when you go through the output that produces loss going forward. So what are the things you can run into? After many iterations, even though there is supposed to be an aggregation of previous information. Since the activation tan H is only between -1 or 1, and sigmoid is between 1 or 0 and 0, the activation is always going to be reducing the previous information by a factor that's less than 1. Over a lot of iterations, if you multiply 0.99 to the power of something, even 0.99 will get small after some iterations. So even if you're maintaining a lot of the information, it might not get through because it won't carry all the information through, and you end up having RNNs that can only go so many steps before the information is diminished from the 0th input. So it might forget by the 5th output. In the back propagation direction, it's the same thing, where the gradients may not be passing their information back through to teach about sequential dependence. Sometimes there is an exploding gradient, but it's not, I don't think it's likely because the derivatives of the activations that produce the gradients are between 0 and 1. So there are different architectures that try to take on these problems like LSTMs and GRUs. And I want to highlight the LSTM on the bottom here and how it tries to handle these problems. If you attended lecture yesterday, you know that the professor goes through all of the math inside here and teaches it well. So, so what I want to highlight here is the top bar that passes through. What's happening here is that it's maintaining this line all the way through, like a kind of like a skip connection, or like almost like an identity, but it's not quite, where you're trying to pass the information directly. It's like a highway with a few operations where the information that you want to remember will be maintained for much longer and continue forward. And the gradient propagating backwards, the gradients you want to maintain will also be propagated backwards. There are certain terms in the math that tells the network which terms to forget, depending on importance, and the network doesn't always replace what's in this highway, and it will maintain the most important parts in this hidden state highway. Okay, moving on. Let's look at some issues to consider during training. So one thing that can happen is a lack of exploration, where what might happen is that one of the probabilities of the words will be so high that it won't ever see whether or not another word could be used in that location. If you, for example, in the lyrics, never gonna give you up, never gonna let you down, a situation where it only learns that up is correct because it learned it first and made its probability value so high that it never learns down and never gets feedback from it. It's not exploring what other words are there. And so you can address this by introducing noise into the probability distribution output before they're passed to the max part, so that the output will have the correct probability distribution plus noise to have it start trying different things that might be almost as probable and avoid getting stuck in a local optima. There's also teacher forcing. Going back to the generation example, so say that H2 was slightly off and it got the wrong word at this location. The network can then really easily go off in a strange direction in the language model and start to not make sense or repeat itself. And it can have trouble recovering from this wrong word choice, in this case here at H2, and it will have trouble learning because of it. So there are different methods that people have come up with to handle this kind of situation, and teacher forcing is one of them. At the beginning of training, when the probability of choosing the right word is very low, you can put in the ground truth, which is this light gray portion below. And you can put the entire ground truth phrase and try to force it to learn the correct things by forcing it to take in the correct inputs. So that's teacher forcing. You're just forcing it to do the right thing. So for example, in your homework, you could start with 100% teacher forcing, feeding from the ground truth 100% of the time, and then gradually reduce the teacher forcing rate. And the more you're able to reduce the teacher forcing rate, the closer you're able to make the conditions during training time like the conditions during inference time. There are other issues like long-term dependencies being reduced or lost, but you'll learn about this and the solution to it, attention, in upcoming lectures. And then Parshit's gonna talk a little about dropout to address things like overfitting before we go to the code.
All right. Thank you, Mia. So just one thing to point out with what was covered in the previous slide. So you saw teacher forcing. I'll recommend you to just review that again after going back, because that is a very useful component for homework 4 part 2. So things that are being covered here are useful for both homework 3 and 4. So please keep these things in mind. So the next thing is to address overfitting, right? So the most common thing that we've been doing so far to address overfitting in different networks has been dropout. So that is a different, it's a little different in sequence models. So PyTorch out of the box offers you a simple naive dropout where basically, there are two dimensions to this entire thing, right? It's the same network, but it is applied on different time steps. So the naive dropout that is offered by PyTorch, it basically applies the same dropout. It applies a different dropout mask to different time steps. And this dropout mask takes place or takes action only between different layers of LSTM and not between different time steps. So if you have two layers of LSTMs, you would take the hidden state at any time step at that layer and you would feed that as input to the same time step at the next layer. So the naive dropout offered by PyTorch takes place between different layers of LSTM. So if you specify a number of layers at one, there is no dropout, irrespective of what dropout probability you specify. So this is naive dropout. It has a different mask at each time step and only between different layers. So only in the input-output connections of LSTMs or RNNs or whatever. There's a slightly better version called log dropout, which applies the same mask at all time steps. So irrespective of the length of your input, the same mask gets applied to all time steps, but it is still only on the input-output connections, not on the recurrent connections between time steps. There is an even better version, which is called variational dropout. This was proposed in 2015. So the figure here is from, so in variational dropout, you have dropout both on the input-output connections and on the recurrent connections, and the masks are also the same. So in this figure, the solid lines represent dropped out connections. So in the naive dropout RNN, you can see that the solid lines are all of different colors, which means different masks, and they only go up and down, which means they are only between the input-output connections. In the variational RNN figure, the solid lines are all across. So they are between recurrent connections and between input-output connections. And they are also of the same color and same directions, which means same mask at each time step. So log dropout will be a useful tool for you in homework 3 part 2. Unfortunately, PyTorch does not have an out of the box implementation, and the one provided by Torch NLP would not suit the shape of your data. If you just use it directly, it would just act like naive dropout. So we would strongly recommend you to read that implementation, understand what it is doing, and implement it according to the shape of your data, because the shape of our data is always batch size being the first dimension. So you have to adapt the code in some way. So yeah, this was about regularization. Again, this is a very useful tool that we will be using a lot. So this is the theory component. We'll be going over a code demo to see how RNNs can be implemented. But do you have any doubts so far? Take that as a no. Okay. Okay, let's go through a small code demo. So this is basically, in the beginning we covered there are different kinds of modeling that you can do. One of them was many to one, where you have a whole time series input and your task is to give one output for it, which is like sentiment classification. So in this example, we have some reviews of movies. What we'll be doing is taking those reviews and predicting whether it was a positive review or a negative review. And we'll be using LSTMs for this purpose because, as Mia mentioned, vanilla RNNs have certain problems and LSTMs help avoid them to a certain extent. She also mentioned that we have this concept of embedding, because if your vocabulary size is too large, like here it's a 74,000 word vocabulary, you cannot represent a word with a 74,000 dimensional one hot vector. That is like too many features to be dealt with, and that's too high a space to be learned in. So that's why we'll be using something called an embedding layer, which is offered by PyTorch. It basically offers you a learnable embedding where you map the 74,000 vocabulary to a lower dimensional feature vector.
Harsha, could you share for the recording on Zoom?
I'm sorry.
Are you sharing your
Oh,
screen?
you stopped sharing. I'm sorry. Yeah. Okay. Now I am. Okay. So as I was saying, we'll be using LSTMs and embeddings as our primary tools here. So you can go through the notebook in detail. We begin by, I'll just show you how the data looks like. So the data is basically one big file comprising a lot of reviews. So they are like one review in each line. They have punctuations and everything. And then the labels file is also one big file having the words positive or negative in different lines. Uh, there is some data cleaning like removing punctuation, special characters, breaking them into different lines and doing all this thing. And then eventually you basically have a list of reviews and corresponding labels. Now, the thing that we have to do for actually using the embedding is convert these words to integers first so that they can all act as different indices in the vocabulary. So this is what we do in this cell. We first take all the unique words in all these reviews. We create that vocabulary and you can see the number of unique words is 74,000. That's a huge vocabulary. So after that, what we do is all these textual reviews that we had, we map each of the words to the index in the vocabulary. So after doing that, you can see that if the review was Bromwell High as a cartoon comedy, it ran at the same time as something, something, something. Each of these words get mapped to integer indices in the vocabulary. So this is the representation that we'll be using as inputs. Similarly, we also encode the labels. So positive becomes 1, negative becomes 0. So that is what we do in this cell. Finally, we see that we just inspect the length distribution of these reviews. So as Mia mentioned, all these networks, they suffer from a vanishing gradient problem. So if you have huge sequences, you can end up actually losing information from the initial part of the sequence. And reviews generally have a lot of useful information in the beginning, and that is a good indicator of whether they're positive or negative. So having super long sequences is not a good idea. And if you look at this data set, there are some sequences which are even more than 800 words long, which is like too big. So if you look at the distribution here, you see that most of the reviews are under 200 words long. So that is a good place to truncate all the reviews uh, because in the initial 200 words, you'll mostly have some information. So that's what we do at this point. And finally, we are ready to do our modeling. Okay. So this is another important part that you will be doing a lot in homework 3, which is padding. So for reviews which are under 200 words long, so you basically feed an entire batch to a network, right? So while RNNs can deal with sequences of different lengths, one batch must at least be of the same length. So if one batch has reviews of size 100, 150, and 200, all of them have to be brought to the same length of 200. So that is why we use padding. We basically pad the entire thing with zeros, the remaining part of it. So if there is a sequence which is of less length. So if you take like 5 sequences and you make them into a batch, so you can see one is of 140, one is 200, one is 150, and you use the pad sequence command of PyTorch. So you can use this out of the box. You will have sequences which are all of 200, and you can see that the latter part is all zeros. So this is zero padding. So you will have to use this to create batches. And PyTorch has a function called collate function, which you can implement in your dataset class, which basically what it does is it does some pre-processing on the batch before returning it as a batch. So the get item function keeps returning items and the collate function basically creates a batch out of them. So when you create a dataset class, you will basically in the collate function, you will do the padding thing. So once you have different reviews and different corresponding labels of that batch, the collate function basically gets a list of all these reviews and all these labels. And then to return them as a batch, as a tensor batch, you have to pad them. So that is what pad sequence does. You pass in it a list of indexes, which is basically a list of reviews, and they would all be padded to the maximum length, to the review of the maximum length. So there is a small example which is given above this, which is a small batch of just 5 reviews. And finally, the padded sequence is a tensor of sequence length 200 because that's the maximum length in the batch. So you will be using the exact same thing in the dataset class. Once you have the dataset class, you can just create data loaders. you will be using almost the same code in homework 3 part 2. So you should refer to this later as well. In the data loader class, only one thing changes from the data loaders that you've implemented so far. You pass an explicit this custom collate function, which is a part of your dataset class itself. So the default collate function is to take all the list of all the items in that batch and return them as a tensor. But here you have to do some pre-processing before returning, which is padding. So that is why we have this custom collate function. Once you have this, you can look at some. One important thing is that different batches can be of different lengths. That is the benefit of RNNs. You can deal with sequences of different lengths, but one batch itself has to be of the same length. So you can see some sample outputs. If the 256 is the batch size, the maximum size is 200, and then labels are just single integers for each element in the batch. Finally, the network. So as I said, the network will have two main components. One will be the embedding layer to map this huge vocabulary into a lower dimensional vector, and the second would be LSTMs. So you initialize all those things. So first is the embedding. You just use PyTorch's embedding. You pass two things into it, the vocabulary size, which was 74,000 as we saw, and a lower embedding dimension. So I think here we are using 256, oh, sorry, 64. So that is what you pass yours, which means that each word would be mapped to a 64 dimensional vector. Then we have the LSTM. The LSTM has a dimension of the hidden state. The hidden state is the state which keeps recurring. And that is also the output of one LSTM layer to the next LSTM layer. So PyTorch's LSTM takes these arguments. First is the embedding dimension, which is basically the input dimension. What is the size? What is the dimensionality of the input that goes into the LSTM layers? Then there's the hidden state dimension. Then is the number of layers. So if you specify n less as 2, which means two LSTM layers stacked on top of each other. Then you can have dropout. As I said, this dropout is the naive dropout taking place between LSTM layers. And finally, bidirectional. So I think in the lecture it was covered that you can also have bidirectional RNNs, which basically have context from back and ahead of the current time step. So this is what bidirectional RNNs do. So they have, if my hidden dimension size is 100, there will be a 100 dimensional hidden state from the back and 100 dimensional hidden state from the front. So the final hidden state that will go into the next layer is a 200 dimensional thing. So that is why after I go through my LSTMs, I have a final linear layer to map my final output to two classes. So even though my hidden dimension was like this variable hidden dim, since it's bidirectional, the final output will be twice the size, one from the back and one from the front. So that is why the linear layer maps 2 times hidden dim to output size. The forward method is pretty straightforward. So this is how we initialize it. The vocabulary size is a total of one additional token apart from the vocabulary, because now we have tag tokens as well, which was zeros. So if you look at the pre-processing part, the vocabulary starts with the index of 1. The index 0 is reserved for pad token. That is why the vocab size here is len of vocabulary plus 1 for the pad token. The output size is 2 because there are two labels, positive, negative. As I said, we are mapping this 74,000 dimensional vocabulary to vector of 64. That is why embedding dimension is 64. Hidden dimensional 256. It's bidirectional, which means that the output would be 512 dimensional. And finally, we have 3 layers of RNNs. So there are 3 layers stacked on top of each other. There's dropout between each layer. So there are 2 dropouts. And the probability is 0.4, which means like 40% chance. This is typically very large. You can play around with these hyperparameters. Finally, you create the network. You train it very normally, cross entropy loss. Okay, one thing which I forgot. This is many to one, right? So it's the final time step final time steps output that has seen all the inputs in all the words in the input. So it's only the output of the final time step that matters for the purpose of classification, right? So what we do is, while this LSTM, while this network would give some outputs of 2-dimensional at every time step, we only care about that output at the last time step. So when we return from the forward method of this network, we only return the output of the last time step. So the dimensionality of the data is batch cross time steps cross some dimension, right? So in the case of output would be batch cross sequence length cross 2, but we only take the last time step. So that's why the -1 in the second index. After you have this prediction, You can easily use cross entropy laws between this two-dimensional prediction and your labels. The train and validate functions are pretty standard, what you've been implementing so far. And you can, of course, try to train this network. You can do some hyperparameter tuning and see what effect the dropout has, the number of layers have. Again, very useful because you will be doing the exact same thing in homework 3 part 2, but not for a many to one case. It will be many to many case. After this, I mean, we just have test functions, and you can see that it reaches a decent accuracy, 75%, and you can pass some test reviews. You can create your own reviews by passing it and see that it is fortunately giving the correct output for a negative review and a positive review. Yeah, you can go back, look at this notebook, try changing hyperparameters, and specifically see how the dataset and network classes are framed. Because again, you have to do the same thing in all homeworks now. Any doubts with regards to the code? Yeah, yeah, that's arbitrary. So that's a hyperparameter. So this case, the dataset is very small. There's 2000 reviews in the trained dataset. So if you create a very big network, it probably won't converge. Right? So I tried with 128, 256, etc. It was just too big an embedding to be learned. So the embedding is basically a learnable vector for each word, right? So it's a matrix of 74,000 by whatever your embedding size is. So it's 74,000 times 1024. That's a huge matrix to be learned with very little data. So that's why you had to keep all the dimensions small. Typically, it's not 64 dimensions, 5 and 2 dimensional, something bigger when you have more data. So the purpose of the embedding layer is basically to take some low dimensional data or some unsuitable dimensional data to some decent or acceptable level data before feeding it into, say, your RNNs. So in the case of MFCCs, each time step had 28 dimensions. Remember, it was a 28 dimensional vector for each time step. It was too low dimensional to be fed into an LSTM and learned. So in homework 3, you would actually not be using this kind of embedding because you don't have to map integers to a vector. You have to map a vector to a vector. So there you would be using a 1D CNN, in fact, to increase those 28 channels to more channels, say 256 channels, before feeding it into an LSTM. But if it's a text case where you have to map integers of a vocabulary to vector, you can use PyTorch's embedding layer, which you will be using in 4 part 1. So there are different kinds of embeddings, but the purpose is the same, to bring the data into some acceptable dimensionality before feeding it into a sequence net. Okay. Anything else? Okay. Mia, do you have anything to add?
No, that's all.
Okay. The notebook and the slides are on the Piazza post, so you can refer to them later if needed. And we'll be continuing with the hackathon now.
Thank you.
Okay. Thank you, Mia.